name is Yoon Kyo Jong and I will talk about our paper, Face Reconstruction Transfer Attack as Out-of-Distribution Generalization. Our work addresses face template attack, also known as face inversion, which attempts to invert the feature embedding stored in a target face recognition database back to its corresponding image. Previous works, however, successfully passes the verification test well on the target/scene encoder but tends to fail passing on unseen encoders, or systems, despite the image quality looks decently good to human visual perception. We denote such tasks as transfer attack scenario. Such transfer attacks are critical due to the nature that a single invaded system might expose every other systems in danger in terms of privacy issue. Transfer attack is not addressed thoroughly in many previous works, and poor performance on unseen encoders is related to out-of-distribution generalization task. Therefore, we bring up a transfer attack method in an out-of-distribution generalization perspective where we aim to generalize the generated image on unknown face encoders where we do not have any information of. Please note that most of the out-of-distribution generalization focus on training and generalizing a neural network to unseen images, while our work focuses the other way around, which is generalizing the generated image on unseen networks. Our work highlights the out-of-distribution generalization perspective solution for face transfer attacks and suggests averaged latent search and unsupervised validation, ALSUV, which outperforms previous methods both on seen and unseen/transfer attacks. We also conduct in-depth analysis on our method to investigate the effectiveness of the components of our methods. First of all, the basic structure of our method is optimizing the W space of pre-trained style GN2 trained with FFHQ256 dataset with cosine similarity as the loss function between the target feature and the generated image from the latent to optimize as shown on the figure on the right side. Naively optimizing a single latent doesn't guarantee optimization close to 1, as we can see in the red histogram on the left figure. We term this as an underfitting issue and suggest the first component of our method, which is optimizing n differently initialized latents and generating multiple images. Then we can select the sample where the encoded feature is closest to the target feature. This way the final attacked feature mostly has cosine similarity close to 1, which is shown in the blue histogram in the left figure. As we solve the underfitting issue, we also face an overfitting issue. Naively selecting the rank 1 sample of which feature is closest to the target feature causes overfitting, which can be observed in the coral color bar plot as the rank 2, 3, and 5 shows better performance than rank 1. In order to resolve this, we suggest latent averaging and unsupervised validation with pseudo-target using a surrogate validation encoder. Latent averaging is done by averaging the latents throughout optimization steps as shown in the equation. Next, unsupervised validation is done by the following process. First, we get the K_bar top features comparing with the target feature as the candidates. Secondly, we forward the candidates through the validation encoder and average them, which works as the pseudo-target. Finally, we select the image where its feature is closest to the pseudo-target. In this slide, we compare the results with previous methods. We use 6 different types of face encoders where the backbone networks are different, training loss function are diverse, including triplet loss, cosine face, arc face, and etc., with 3 different types of datasets, which are LFW, CFPFP, and HDB30. We sampled 200 identities from each datasets and compared the success attack rate, SAR, which quantifies the ratio of success attacks. Success attacks are based on verification between a real image with the same identity, but not the one used for target. Our method is highlighted with gray cells, and the red cells indicate that the target/scene encoder is the same as the test encoder. As shown in the table, our method surpasses every previous methods despite the model and dataset. Previous works only measured SAR, but we conduct identification rate, which is the ratio of successful retrieval given a database/gallery of face embeddings. We compose the gallery with real images and probes with the generated attack images. As shown in the table, our method also surpasses other previous methods. We also conduct ablation study on each of the components. We vary the number of latents and compare the SAR for transfer attack scenario when latent averaging and unsupervised validation is applied or not on the 3 datasets. We can observe the significant improvement of each components, especially for the number of latents, which shows the largest improvement. It is known that flatter minima point contributes to out-of-distribution generalization. We provide both visually and quantitatively analyze the effect of latent averaging to flat minima point. First of all, we visualize the loss surface in 3-dimension, and the contour plot on the first row for the target/scene network and applying latent averaging shows significantly flatter surface. Secondly, we measure the first eigenvalue and trace of Hessian matrix of the scene network, and latent averaging shows lower values, meaning flatter surface in the minima point. This leads to lower loss for unseen networks, which can also be interpreted as better generalization. We analyze unsupervised validation in this slide. We compare the cosine similarity against the ground truth target feature with the scene/target network's top 1, our suggested top 1 with unsupervised validation, and the pseudolabel generated during unsupervised validation in validation encoder space. Pseudolabel shows the highest similarity followed by our method and the scene network's top 1. Please note that there isn't a corresponding image of the pseudolabel, hence is not available to use as the attack image doesn't exist. We also compare the cosine distance of scene network's top 1 and our suggested method's top 1 in the unseen encoder space where our method shows higher scores. Finally, we vary the type of models for validation encoder where we find a positive correlation between the encoder's general performance and SAR. On the bottom, we show some sample images of previous methods and our method for qualitative comparison. Thank you very much for your interest to our work.